All right, so we have another tank problem similar to the previous parts A and B. What we're interested in, so let's just walk through this, read through our word problem. Um, Similar heated tank, just one this time, with a cross-sectional area of 1 meter squared. And we have a drainage hole as well, 0.05 meters squared. So pretty similar assumptions we can make with what we did with Bernoulli's equation and how we derive the outlet flow with respect to the velocity and height term. And then what else do we have? So now since it's heated, we have some more energy going into the system. We have that steady state water flow or inlet flow, a volumetric flow of 1 meter cubed at an initial temperature at that steady state. And then we have our heater putting in some uh, power at that steady state as well. So let's go ahead and draw this out so we can kind of visualize what we're looking at here. So we have another tank, Q inlet flow, our volumetric flow, as well as we're going to assume this is a perfectly mixed substance, and that'll make more sense later. And then we also have our heated coil adding some power to the system. And then again, our drainage hole, Q out, and we can label our cross-sectional areas here. We're going to assume the cross-sectional area for the tank is uniform throughout the different heights. We'll see in our calculation, and then our drainage hole, AH. Let's go ahead and label our height as well. Change in height, that'll be important. And we also have a temperature inside our tank, T. So we can kind of go ahead with what we did earlier with the previous tanks, how we used Bernoulli's equation. If you remember, we derived our change in height with change in time. Well, actually, let's start with our volume is equal to our cross-sectional area times our height. And then when we derive this equation for the right-hand side, our change in height with change in time, dH over dt, we eventually found that it was equal to 1 over our cross-sectional area times our inlet flow minus our outlet flow. So the difference in our volumetric flow rates. We also remember with Bernoulli's equation, the actual substitution we made with the outlet flow, and that was our our drainage hole times the square root of 2gh. So if you don't remember, pause right now and kind of go back to that previous video. But these were the terms we found that pretty much identical across those tanks. So we'll be using those again. But what's more interesting now is now that we have a heated coil, there's more to account for in our energy balance. So let's go ahead and do a internal energy balance. If you remember the first law of thermodynamics, we have our change in internal energy is equal to our heat, our enthalpy, and our work in our system. And we're going to go ahead and assume that there is no work being done on or done by our system. So that term becomes 0. And now we just have our internal energy is equal to our heat. And remember, for this tank, we're just going to be using water. And because of that, it's just going to be water in, water out. We're not going to be boiling that water. So pure sensible heat. And we'll be using the equation. Well, what is the energy of water being heated in the tank? And we also have to account for that heated coil element as well. So trying to write this out, well, we remember what is the energy of a heated component. Well, that would be our kind of, I don't know how we want to go about this, but yeah, let's just go like this. So our heated element, the energy of heated component in our system is equal to its mass times its specific heat capacity. So this would be water, and that would be times our the difference in our relative temperature with respect to well, the difference in temperatures with respect to a reference temperature. And we're going to go ahead and say our reference temperature is 0. So I'm just going to put T. If you remember, it would normally be something like a change in temperature. And so it would be our difference in temperature minus our reference. And if we say our reference is 0, that term simply becomes T. So that's why I'm going to write it like that. And yeah, we're going to go ahead and do this for the left-hand side, and try to keep on defining our variables here. And this will be the other differences in Q for the entire system. So the left-hand side is just a sort of generalization, and then we'll kind of be deriving more of that as we go on. So let's keep on doing this with what we have. So mass, our mass, well, we don't have a given mass, but we do have some variables we can work around. If you remember what we do have, we have a volumetric flow rate. So volumetric flow rate, I like to write it as that, and that would be a meters cubed per second, and that is actually our Q. And well, mass and volume, how does that relate? Well, we have a density, and density is equal to mass over volume. Actually, I think I'm getting a bit ahead of myself. So this will actually be used for this inlet flow and outlet flow. We have two different volumetric flow rates. Those will be used in our right-hand side for defining the rest of our energy components. But I guess that's important to remember for now since we'll be using it later. But in terms of what we do have for the left-hand side, our mass, what we can define, will do something like our mass is equal to our volume. Oh, so, well, it actually is a pretty similar concept, but mass is equal to our volume times our density. And instead of breaking down our volume over here, we will just keep it as volume, since if we remember up here, our volume was equal to our cross-sectional area of the entire tank times our height. And that will be very important later on. So let's go ahead and do that substitution. So our mass is equal to our volume. So our volume is this term. Volume is equal to our cross-sectional area times our height. So cross-sectional area times our height times density. And then we can go ahead and make that substitution back into our initial term for what we wrote out for the heat of the entire system. So I'm going to go ahead and write that out. And since this is a differential equation, we're going to go ahead and add our derivations for the dependent variables with respect to time. So I'll just kind of do just group everything together here so we don't have to rewrite more than we have to. So we have our mass substitution, and that is volume times our density, and that will be the volume was substituted by this cross-sectional area times height. So I'll just go ahead and write this as our substitution for our mass. Then we still have our specific heat capacity of water times our difference in relative temperature with respect to a reference temperature that was 0. And all of that is respect to time. So that's our left-hand side. A little complicated there, and we can kind of simplify this out so don't have to worry about it later on. So taking out the constants, well, we know our cross-sectional area is constant. Our height is actually changing, and our temperature is changing. So we'll keep those under the derivative. So those will be our two dependent variables in this differential equation. And then we have our density and our specific heat capacity as constants. So we'll go ahead and pull out the constant terms and then rewrite our derivative like so. And then now we can begin to define the energy on the right-hand side. So all the system components that are being defined by this energy balance. So this is the total energy of our system. Well, I mentioned earlier we have our heating coil providing some power, and that power was the heating power of 20 megawatts. So that is an input of power. So I'm going to go ahead and define it as Q, big Q, for watts. And remember, watts is joules per second. That'll be important for kind of breaking down our units for the other components, our volumetric flow rate related components. Kind of deciding if I want to keep it as big Q for now, but yeah, let's just keep it big Q for now. So that is the heating component of our, what it is, the energy of our heating component being added to the system. And then what do we have? We have our two other volumetric flow rates, and those will be concerned with what I mentioned earlier about how we had to define our volumetric flow rates in here and relating that to our mass once more. So we'll do something like our initial flow rate going in. So that is, remember, that is a volumetric flow rate, meters cubed per second. And if we want to substitute that for our mass once more to get a more specific term of our energy component, we have to multiply that by a density. So volumetric flow rate over here times our density is equal to our mass. So we'll do Qn times our density of water. And what else are we missing? Well, now we have the mass component. Actually, let me write this out. So density is kilograms per meters cubed, and that will cross that out. So now we have kilograms per second. Well, if we want to get to joules, trying to match this term of Q to joules per second, well, joules comes from our specific heat capacity component, C, or specific heat constant, sorry. So that is joules per kilogram per Kelvin. And then, well, all we're missing to get rid of that Kelvin is temperature. So very similar to how we kind of shuffled around our substitutions here for the left-hand side, we're doing the same thing for our right-hand side and defining those with our inlet and outlet volumetric flows. So this will be Tn corresponding to our Un volumetric flow rate. And let me double check, make sure we got everything. So we have our mass component, and then C, our specific heat constant, and then T. All right, awesome. And then we'll subtract our outlet flow since this is going out compared to the inlet flow going in. So this is energy leaving the system in the form of the temperature of the water, and that will be in joules per second as well. So let me actually show this kind of crossing out of units. So meters cubed, kilogram, kilogram, and then Kelvin, Kelvin. Now you're just left with joules per second, which does match with our watts from the big Q of our heating component. So that was the energy going in. Now we have some energy going out, and that is pretty similar to our energy going in, except now it's a volumetric flow rate going out times our density times specific heat capacity times our temperature out. Now what's important is I actually didn't write temperature out, I wrote T. And that kind of goes back to how I mentioned earlier that this is perfectly mixed, a well-mixed tank. And what that means is that all of the area within this tank is the same temperature. So all of that is the same temperature. That's what it means to be well mixed. And so because of that, we can say that the temperature of the water leaving at this hole here is the same temperature as the water throughout the entire tank. And that's why I can keep that as T. And that's very important because we actually we'll get a different solution altogether if we actually wrote T out. And if that was different from our T on the left-hand side that we're doing a differential equation for, having a dependent variable of temperature with respect to time. So it's a good thing we actually have our T here. And I believe that is all for our system components. So let's go ahead and start simplifying this. So if you kind of see some components canceling out as we simplify and try to isolate our left-hand side with just our dependent variables with respect to time, since, again, like the previous problem, we'll be doing using a function in Python to solve the right-hand side and get those dependent variables and return them as results. So yeah, kind of isolating, we come across I guess we can just kind of divide across and isolate here. So I'll just rewrite this. Yeah, let's just rewrite this, and we'll do some more work with that derivative later. So we have our derivative, and then we're dividing by all three components: the cross-sectional area, the density of water, and the specific heat capacity of water. So kind of looking across, so what I write just doesn't come out of nowhere. Q actually doesn't have any of those components, so we'll be dividing all those by Q by all of those components. But in the inlet and outlet volumetric flows, you can kind of see we do have some components that are identical. So those will cancel out. So I'll just do something like, let's see, everything will be times 1 over our cross-sectional area. then big parentheses Q, our heating component from the heating coil, will be divided by our density and our heating capacity. This will be added to our inlet flow, the energy going into the system, and that is just our Q in times our temperature in, since density and specific heat capacity are being divided out. And then very similarly, we have our outlet flow, Q out and T. Okay, so what you might be wondering is, what do we do with that kind of two dependent variables in our single derivative? Well, if you remember from the previous problem, we actually already have dH dt. So we can actually do a substitution there if we can kind of isolate it out from our left-hand side. And if you remember our calculus, some basic calculus, this is actually a product rule, the product of two dependent variables with respect to an independent variable. So what I'm going to go ahead and do is do just that, the product rule. So I'll take out derivative h and then keep our temperature. And then same thing, but opposite, I'll take out our temperature and then keep our derivative height with respect to time. So that's just basic product rule. And now we can actually do our substitution with dH dt, since we actually already derived that earlier from the previous problem. So once more, rearranging some more algebra, I'm kind of going to go ahead and simplify this so I don't have to rewrite too much. But we want to isolate, again, our temperature, since we already have the derivative for height. So rewriting this, we have our temperature with respect to time is equal to 1 over our height, and then kind of copying down what we have earlier from over here. We also have our 1 over our cross-sectional area, and then keeping everything the same within these parentheses, heating component with the heating coil over our density times C, specific heat capacity, the difference in our volumetric flow rate energies, and difference in our volumetric flow rates or energies, that is times T. And all of that is still times the 1 over AC. But in addition to that, we subtracted our derivative with respect to height term. So this will be minus T dH dt. And all of that is still, we're being divided by our height. So yeah, kind of isolate all of that now. So what else do we need to do? If you remember from the last problem, we're going to be using solve IVP, solving an initial value problem. Well, we need an initial value for our terms, so we need some sort of way of representing our initial height and our initial temperature, which we'll be plugging into our function solve IVP from scipy.integrate. So let's go ahead and do that now. I'll actually copy down our dH dt term, so we don't have to kind of go scrolling for that again. So dH dt, I believe, was our Q in over AC squared times 1 over 2g. Let me make sure that is correct. Q in. Did I do that correctly? I mean, I can go ahead and derive it if I kind of get it wrong anyway. Yeah, let's go ahead and derive it just to make sure. So we'll be using our dH dt term and substituting our Q out for the equation we derived from Bernoulli's relating our pressure, height, and velocities. And since this is at steady state means that there is no change in height. And later on, this will also mean that there's no change in temperature as well when we do our the other equation and solve for the initial temperature. So let's kind of just take things slow. Our full equation would be 1 over our cross-sectional area times Q in minus our outlet flow, which was the drainage hole cross-sectional area times the square root of 2GH. Again, that was the substitution, the outlet flow for Bernoulli's. And we're going to go ahead and isolate. So Again, at steady state, dH dt is equal to 0. And what that means is that we'll rewrite this in isolate for, and remember this will be terms for the initial value, since this is that initial steady state of 0. So we'll actually be using inlet flow initial, and then within this, after copying out this outlet flow term, we'll be using the initial height, and that's what we're actually solving for. So if I remember correctly, isolating our constant multiple on the outside gets canceled, and then we have something like Qn AH cross-sectional area squared. Yep. Oh, see, I was wrong. It is not AC, it's AH. So good thing I derived that. All right, so we'll be using that as our initial height term. I could have just gone back, but that's whatever. And then we'll be using that to plug into our temperature here. But other than that, let's do our temperature. So our temperature was that whole term. Just kind of looking at it, we know, well, we have the same assumption. dH dt is, or I'm sorry, the derivative of temperature with respect to time is equal to 0. So since these two values are 0, let's go ahead and make those substitutions. So it will be 0 is equal to, just trying to see if you could see that. Actually, I'll just show it. So this value will be equal to 0, and this term is equal to 0, because our derivatives are equal to 0, there's no change. So kind of rewriting, we have 0 is equal to, well, actually don't need to even write those constants, since remember, when we multiply a constant term across all the terms, it cancels out as we're trying to isolate. So I'm going to go ahead and say that these terms are actually 0, and we're going to be isolating for our T initial here. So I'll go ahead and write it out as our heating coil component, energy component, divided by our density and specific heat capacity, plus our inlet flow initial times the temperature inlet flow, temperature of that inlet flow initial, minus our outlet flow, again initial, and times our T. And remember that the outlet flow, we have this same substitution we make as we derive from Bernoulli's. So doing some isolation, almost a little easier than the height one, but so since we're isolating T for our initial value, that should be T initial. So at steady state, our T initial is equal to 1 over our outlet flow, our volumetric flow, and parentheses, yeah, we just rewrite it as is. So heating component divided by density and specific heat capacity plus our inlet flow initial. Oh, I should mention this is also initial, since those values will be changing. And we want to make sure we are at the initial steady state. So keeping all those constants with what they were in the initial steady state. And I believe that is it. So I'll be referencing all these equations. I believe that we have everything we have. We have our given constants from the word problem, and then our 4 equations that we derived. 2 being the height, the initial height, and well, the derivative, our differential equation for height, and then the 2 for our temperature, and the differential equation for temperature, and our initial temperature. So now that we have those models, let's go ahead and code this in Python. I want to check. Yes, this is just one part, so no cuts. I think I did the last video in a full cut, so yeah, close that stream. Leave, is it just this? Yes, okay, and switch that off. Okay, cool. So now we are with our, what's it called? Or we're on Google Colab. So this is what I used to write Python last time. I'm going to be doing the same thing here. I don't know if I want to keep on switching. I should be able to switch to our, let me see, our, yeah, OneNote here that I was writing out. So that should be fine. All right. Yeah, let's go ahead and do this problem. So we have, what was our problem? Where are we? Here. Okay. So our problem is a heated tank. Go ahead and name that heated tank and start coding. So kind of doing our basic imports as we did last time, importing numpy as np. I believe in this case we might use square root and some other algebraic functions. So, just nice to keep it simple as a shortcut. And then I'm using scipy.integrate for our solve IVP. So it is from scipy.integrate. So we'll be integrating the differential equation. We want to import the function known as solve IVP. And then since we're going to be plotting these, I believe that is the next part. Yeah, this third part. So now there's a change from our initial steady state, and we want to calculate and plot the new temperature and heights. And that's what we'll be using from Plotly. Is it subplots, I think? And import, I think it's make subplots. So we're going to be making those subplots. Hopefully it doesn't yell at me. Maybe. Please. Okay, awesome. So yeah, let's go ahead and define our variables here. This is just kind of copying straight from the word problem. We have cross-sectional areas, two different ones, so let's go ahead and do that. I think I called it AC. Yeah, let's keep it consistent. So AC is 1 meter squared, and then we had our cross-sectional area. So that was for the tank. AH is for our drainage hole, and that was much smaller. Remember, that's what allowed us to make our velocity 2 and our Bernoulli's equation pretty much 0. Or I'm sorry, the velocity 1 term equal to 0 since these cross-sectional areas are so different. Almost like a magnitude of what? Is that 100? So yeah, that's what allowed us to make our outlet flow kind of derivation. So let's keep going here. We have an inlet volumetric flow of 1 meter cubed. So Q initial 1 meter cubed, and per second, yep, volumetric flow. And then that was at an initial temperature of 350 Kelvin and 20 megawatts for our heating coil. So I already forgot 350 Kelvin and our heating power of 20 megawatts. So I'll call that Q, big Q. Oh, what's happening here? Sorry, there's a weird keyboard I'm using. Big Q for our heating element component from the heating coil. Big Q initial. And that was 20 megawatts. So 20 megawatts, keep it watts. So we're still in joules per second. So 20 times e to the 6, and that will just be watts. So 20 megawatts. So yeah, we derived those two differential equations and the initial heights. So we'll go ahead and keep on defining our constants. I believe, what else did we use? I think G, here we go. So we used we have G from outlet flow, I believe. Yep, G, we have height, well, that we're going to be solving for that. Cross-sectional area we have, so let's just put in a G for our gravitational constant, 9.8, what was that, meters per second squared, acceleration, right? A density of water, call it rho. We don't just put P. Rho is 1,000 kilograms per meter cubed, I believe. Hopefully I don't get my units wrong here. Actually, I wrote them out earlier, didn't I? Yeah. Look, yeah, kilogram per meter cubed, and we had our volumetric flow. Yes, specific heat capacity, that's the one. Big C, and I think we used 190. Can I use 9? Okay, 90, and that was per joules per kilogram. Man, this keyboard sucks. joules per kilogram Kelvin. And we do have temperature. Yes. Okay. And shift enter. Go ahead and define our right hand side. Well, do we want to call it right hand side? Let's just call it the heated tank. I mean, technically, it is the right hand side will be for both components. So I don't know, heated tank, I guess. And then define our parameters. So if you remember from solve IVP, we need to have a function. Our function is a heated tank, and our function needs to have two parameters. One, the independent variable time, even though if you notice from our derivations, we actually didn't use time, but we'll include that so solve IVP works. And then so time, and then a vector component of our results that we want to return from solve IVP. And those vectors will be our temperature, so T and H, and I'm just going to, what I'm doing is unpacking that vector into two different results. So we have those recorded as we write our equations here. So what do we want to do first? Let's define our Q out, since that will be in our dH/dt term. So our Q out, what did we say it was? Q out is this root, cross-sectional area times the square root of 2g h initial. So cross-sectional area of our hole, right? Times the, I'm doing the MP square root. That's why I imported numpy. And that is 2 times gravitational constant times height. All right, so that's for Q out. Let's also define our dH/dt term. So this is the right-hand side for that term. And what did we say that was? So this is the initial value. Where is it? Am I missing it? I believe it's just this, but let me double check. So this was when we had both. Product rule. I should be a little organized here. Let me stop for a second, find where that is. Okay, so it's actually kind of staring me right in the face. It's this this term here. So 1 over our cross-sectional area of the tank, and then the difference of our Q in and Q out. Remember, this was a substitution. So dH/dt is, I'll do parentheses here, maybe. There we go. Divide that by cross-sectional area of the tank, and then we have the difference of our inlet and outlet flows. And I can just write Q out here since we have Q out up here. Awesome. What else should I do? Can we jump straight into our temperature term? The answer is, I wrote everything out here. I should kind of delete those so we can kind of see our whole equation here. What are we missing? We have height, cross-sectional area, Q. I believe we defined Q. Temperature in. Do we have an initial temperature? Yes. And yes, we should. No, we have our T here. And what else am I missing? Our change, which what's happening is we're going to be changing our heating coil component. It's going to begin oscillating, and then our volumetric flow. So don't think those need to be defined now, but I mean, it's just depending on T, so that needs to be in the function as well. Let's just define it so don't mess up our order here. So Q is 20 e to the 6. So that's just our initial heating component of power. We're adding 10 e to the 6. Looks like that's the amplitude. Yes, times our NP sine. So yeah, NP does all the, numpy does all the out of break functions we'll be using. So sine is one of them. And then we have a sort of frequency relating to t over 20. And it looks like same thing, pretty similar for our Q in that's changing. We have our Q in initial, and is it pretty similar? 0.1 now. So 0.1 times sine of t, frequency relating to t over 100. So remember that, I think it's like a for labeling the trig functions, like a parentheses, b, and then is it, I think it's sine minus c, and then d, something like that. But anyways, the point I'm trying to make is that period is 2 pi over that b term. So this b term is 1 over 20 that we're seeing right now. So if we wanted to find a period, that's how we'd get it. So just a quick aside, more from me, honestly. So yeah, we have our changes. I think we're good to, we might need to put our initial terms somewhere in here, kind of messing up the order. So forgive me on that, but we'll kind of rearrange as we go, I suppose. So yeah, we don't need any initial terms here, so we can just go ahead and do that. So our temperature is equal to, respect to time, the right-hand side of that whole term. Well, we had height on the outside, dividing by height. And inside again, what do you have? Well, we were subtracting, actually let me put it in front here. So 1 over our cross-sectional area. Is that how I want to do it? Yeah, let's do this, divided by 1 over our cross-sectional area, and then we'll subtract out our temperature times our dHdt term, and then inside that, we have our system components Q over parentheses density, so rho times specific heat capacity, ongoing, the difference in our inlet and outlet flows. So Q in times T in minus Q out times T out. So hopefully that's all in. Oh, I see. We need to define our temperatures. So this way we have T in initial. We need T in now, what it changed to. So it dropped from 350 to 340, I believe. So 350, and then, yep, 340. So T in, 340 Kelvin. And what else is that yelling at me for? T out. T out is the same thing as T. So we actually don't need that T. Am I correct in saying that? Let me double check. Yeah, so just T here. There is no T out because it's the same. And remember, our T here is how we did our product rule. So that T is also just a T. I know T outs here. And what else are we doing? I think that's it. So I think we can just, oh no, we need our initial values. So those initial values will be supplied into solve IVP. So I don't know if it makes more sense to put it in the function. Why not? So we have all our initial values. Do we have our T initial? Yeah, here. Okay. Yeah, let's go ahead and define them. So do we have our initial value for height? And my phone is falling. Need like a way to stabilize that. Let me pause and fix this. All right, so that should be good now. What else do we want to do? Yeah, we were defining our initial values, so come on. Okay. So our initial values was our height, our initial height at the steady state of 0. So we're defining that as the inlet volumetric flow rate over our height of our tank squared times 1 over 2g. So height initial, let's go ahead and say, divide by 2 times g, and this component was squared, and it was q in initial over our cross-sectional area, right? overhaul, right? And then our T initial, so that's different from T in, right? Let me double check. I'm not saying anything wrong. T in initial, I think I'm confusing myself here. So temperature initial is depending on T in. Yes, T out is what, I mean, technically it's not T out, but yeah, that makes more sense. So we had a T in initial. We're defining our kind of, I guess, T out initial, but not really. So that was 1 over our volumetric flow rate out initial. So actually make sure, yeah, nothing changed. It was just that value. So when we have our initial value, making sure all our terms are defined as initial. So Q out here. Did I guess I should also define our Q out initial here. Since we have our Q out up top, but we need to make sure this value is using the initial terms, so Q out. Now let me just copy paste it. Since the only term that is changing is that height, we want to make sure that height is from the height initial, which we describe in the line above. So back to the temperature initial, 1 over Q out, and then we had our system components. So that was Q initial, since that value is changing from the heating coil, and that was rho, is it heat capacity? Yes, plus our Q in initial times our T in initial. And did we? No, that's it. Awesome. Yeah, just double checking here. The N, Q over rho. Right, so now we want to actually return our values. So make sure when we return our values that we match the order the vector components were listed in, which was the, right here, our temperature was first, and then our height. So let's do an array just in case. So solve IVP may or may not yell at us if we didn't do an array, but with an array it shouldn't. So we'll be returning dt, our change in temperature with respect to time, and then our change in height with respect to time. So no squiggles, meaning we should be good. Oh boy. 0.1 in valid syntax. Oh, I'm missing the, I think it was a plus, right? Let me double check. So this function, yes, it was 1 plus, so, and 1 was our initial flow rate here. All right, enter. All right, so solve IVP. What does it want from us? So if you actually do a question mark next to the function, I'll give you the helpful documentation page. This is asking us for a function, which we did. We defined our vector, y, and then t, our independent variable. So we want to put in the function first, our time span, and then our as our initial values. So let's do something like our function, heated tank. Then actually I should define our time span, but actually I think we already given our time span, so I won't be having to change it. So it is from 0 to 2000. So if you remember last time we had this t end value, and it's probably good practice to maintain that, but since we're not changing it, I won't bother. So we'll do a parentheses, indicate the range, and it was from 0 to 2000 seconds. That's our range, it's t end. And so that's time span, and then y0, so our initial values, unpack our vector of h naught, or no, temperature, since our function, yep, that's why order matters. So temperature first, so initial temperature, and our initial height, as we define in our function. So go ahead and shift enter, hopefully it doesn't yell. Oh, so I did not define t initial, interesting. I wonder if I'm missing something. Since I did uh, define it up here, so maybe see here. Yeah, I'll go ahead and pause this again to see what the error is here. So the issue here might be that solve IVP isn't finding these initial values since I kind of put them outside or inside the function. So I'm going to go ahead and see, just make sure DTD, our right-hand side isn't depending on these functions. So if I take it out, it should be okay. Yes. Okay. So I'll put it up here right in front and shift enter on both. Yeah, get rid of the indent from when it was in a function. Oh boy, TN. And TN here is defined. Interesting. Okay, I guess we need to just reevaluate everything. Okay, so now it worked, thankfully. So we are retrieving values for our two different arrays, temperature and height. And actually, I want to create our. So since we're graphing it, what we're going to want to do is retrieve those data points solve IPP got for us and plot them using a function, and that is from our dense output parameter here. We're going to set that to true since it's normally defaulted to false. And because of that, we'll be able to have a solution here. Remember that solution function was not there. So if I actually shift entered on this without it, it'll say none. So that's allowing us to use this solution attribute. And we're going to be using that to call our different solutions from temperature and height at a certain t range. So actually what I want to do here is define our not temperature, our time plot. So that's similar how we graphed it before. We created a linear space points using np linspace from 0 to our ending time, so 2000. And let's just, I don't think it specifies how many points. That is not the right one. No, I don't think it does. Okay, so I'm just opening up all the tabs. Here we go. So I'll just say, I don't know, 1,000. Doesn't really matter. The more the better, but don't want to make it too slow. So that's our t-plots. And using our solution function, we can evaluate all the points, all these 100 points, and evaluate them for our corresponding temperature and height plots. So I'm going to go ahead and unpack our array. Since you see we get two different values from our result, we want to make this our temperature first, so temperature plot, and then our height plot. So shift enter on that. Awesome. And then now we can go ahead and use our subplots, so what we were doing before. And since I'm going to be wanting to actually stack these side by side, I'm going to do big one is equal to make subplots. And I'm going to do, I think it's rows first. So rows equals 1, columns equal 1. Biggest column, let's call us. So columns equal to 2. So we'll have them side by side. Oh, it keeps falling. I'll fix that. Okay, should be better. So yeah, we were making 1 row and 2 columns, so we have our plots side by side. Go ahead and add our scatter plots. So this is just adding our data points to the those plots. So we have x was our time, yes, t plot, y is equal to our, so we need to add both, but we'll do t plot first, our temperature plot, and then define our rows. So this is rows. Tell me this is just singular, please. I don't think it'll tell me. Whatever. Rows is equal to 1, and this will be the first column. And then we'll call this, I don't know, temperature, T, whatever, temperature. And I'll go ahead and copy that down, but change around our two things. One thing will change, so the y-axis is h plot, and then this will be our height. And I wonder if I can do this first try. Big one is an update layout, I think. This is more for me, so just kind of some default settings I like to put in. Changing our width and heights to some specified pixels, and then our template. Is it plotly dark? Please be right. Please be right. Oh boy, what happened? So we got something wrong. Here we go. I wonder if it's just row. What is there here? No need to call rows. Might just be row. Nope. Do some live troubleshooting because why not? Wonder if it's still yelling me about rows. Blah blah blah. Bill calls, so maybe it's just singular now. Again. Live and learn? Yeah. What happened here? There's supposed to, oh, it needs to be 2. I stacked them inside the same one. Awesome. There we go. So these are our 2 graphs now. So we see our oscillations, times in seconds, did our range that was defined on the problem, and then we have our, so this is temperature in kelvins. So obviously we decreased to a, so interestingly enough, well, it makes sense since we're changing our heating coil. Now it's oscillating. It looks like it's oscillating to a lower temperature. So if you remember, we went from 350 to 340, but remember that even though we don't have a oscillating function for temperature, it's still oscillating anyway because of our changes in our volumetric flow rate and our heating component from the heating coil. And remember, those are included in our function dt, derivative of temperature with respect to time. So interesting, you see that oscillation. It's kind of like, I don't know, cool little pattern there. And then our height, which was its own function. Remember, it was dependent on our inlet flow. So pretty direct there. Our inlet flow was oscillating. So since our height depends on inlet flow, it's also oscillating. So yeah, I believe that is all of the problem. You kind of get to see all my tabs again. Yeah, so what we went through, we derived our differential equations, the temperature and heights, using our function solve IVP. We had our initial steady state, which we also plugged in, and we modeled our plots, temperature and height, from 0 to 2000 seconds for these changing functions, our Q, heating coil, and our energy of our heating coil, and then Q in our volumetric inlet flow rate. So yeah, that was this problem. Hope that was kind of helpful. All right. Thank you. See ya.